have the protein Acetylcholinesterase. The mutation and chemical change is the binding of serine to the active site instead of acetylcholine, which, if you don't know what acetylcholine is, it is a neutral transmitter. The function is that it hydrolyzes acetylcholine into acetic acid using serine. Then it starts to terminate or destroy the neutral transmission and signaling between synapses to prevent acetylcholine dispersal. And if you didn't know, Acetylcholinesterase is found in animals and humans and is mostly found in invertebrates. Acetylcholinesterase is not found in plants. Serine also acts by inhibiting the enzyme acetylcholinesterase. This protein degrades acetylcholine released at the synaptic cliff. The acetylcholine activates nerve fibers that cause muscle contraction. Here is one part of my model, and then this is also a part of my model. So, the white is the alpha helixes, which is this part. And then the pink is the beta pleated sheets. And then the blue really has no meaning. It's just there to help, put this together. This altogether is just a whole bunch of beta pleated sheets and alpha helix, all connected together, and it's very movable. So behind me is the active site, which is actually found in the middle of my protein, but it is right here so you guys can see it more visualized, because if I would have put it in here, you really wouldn't be able to see what I was doing. So here's like a semi-visual. I don't know if you can really. Yeah. Normally it is found in the middle, but yeah. So this pink part is where the hydrolysis occurs, and this is where the molecule is broken apart, which is right here. And then the blue part, which is right here, is the ionic site where hydrophilic molecules bond. Okay, so this here is my acetylcholine molecule, and I'm just gonna put this right here. If you guys can see my hands on here. As you guys can see here, the purple stick will bond to the ionic site, and the white stick right here will be broken apart and hydrolyzed by water. This is the water. So this here will be hydrolyzed. The white part will be. So yeah. Okay. So acetylcholine will break up into two parts, which this will be the chlorine, and acetic acid, which this is the acetic acid. So we have two parts, and then which these two are both productions of the bonding and hydrolysis, which occur right here and right here. There can also be an additional production of acetic acid that is ionized and will have an extra hydrogen. So what I just demonstrated to you guys is what will be happening if the protein is functionally very normal. And if it's not functionally normal, then the whole structure will be messed up, basically, and it will disrupt the function and the structure. And when the function is not functioning normally, serine is going to bond to the hydrolysis site right here, So if you're wondering why serine is not going to bond to the ionic side, it's because that's where the hydrophilic molecules go, and serine is actually hydrophobic. So it's not going to bond over here. Okay. So, and when it bonds, the acetylcholine will not be able to bond to the hydrolyzed site. The acetylcholine will only be able to bond to the ionic site because the serine molecule is already at the site, which will cause disruption, and the molecule will break apart. The molecule can break apart. In conclusion, the model will not be able to break apart. There could be breakdown of the acetylcholine, but it's just going to be in different portions of the nerve agent, although not much is going to be able to happen because the serine is blocking the hydrolysis site. And then this molecule is going to continue to be bonded. Acetylcholine can only bond to the ionic site, so it cannot be broken down because serine toxin is blocking it. Acetylcholine cannot break down, and there will be issues between the nerve and the muscle cells, which will be detrimental to the body, and the protein becomes less active because it disrupts the entire function. In addition, the proteins become less active because its ability to bond is altered and weakened, and it can only bond to the acetylcholine, can only bond here, can only be bonded here. And then the whole protein becomes weakened because it can't do its function how it's supposed to. So because acetylcholine can't bond to regular sites, it causes a buildup in the central nervous system, which concludes to seizures and cardiac problems and even death. So when serine gets into the protein or acetylcholine, it can be very toxic and can be detrimental to people's health and also, death. So my limitations would be I didn't display the specific functional groups, which is very important because it's what determines the polar and non-polar. Another one would be I didn't put the active site into the protein. Another one would be that I did a simple structure instead of it looking like the glob ones that were also presented online. Thank you for your time. Hope you have a nice day.